Welcome to the Public AI Cafe. Today we present the speaker, Bobby Bahov. He is an AI consultant and researcher with his talk, Building Chatbots Trained on Custom Data. I'm the moderator and cafe manager. My name is Carmen McWilliams, and I'm from Grassroots Arts in Cologne. And I'm partner in the AI for Media research project. This cafe is also part of this research project. Please take notice that this session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speaker expressed their personal view and opinions. This is not necessarily the official AI for Media project opinion. So I welcome everybody who joins today, the Web Cafe. And what are we about? The Web Cafe offers a series of live web sessions, which is taking place regularly. The Cafe is an online forum to gain insights into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. So this is an interactive cafe. So please send us your questions. If you have questions to the speaker, there's a chat box on the right side in this menu. And you may just anytime you feel like send it. And I will read your questions afterwards to the speaker when the presentation has finished. So now to Bobby. Bobby Bahov has over a decade of experience in software product development. He seamlessly navigates the intersection of cutting-edge technology and business efficiency. Starting his career as a software developer, he quickly advanced into project and product management roles. He has managed projects and consulted various clientele, from startups to large corporations, governmental organizations, and NGOs. He has spearheaded multiple innovative ventures and programs focused on AI tools, satellite data, and space technology. An alumnus of the Rotterdam School of Management with a master's degree in business information management, he is currently pursuing a Ph.D. researching AI simulations, digital twins, and synthetic data. So let's welcome Bobby. Are you here? Please say hello. Yes.
Hey everyone.
Hey, great to meet you in the cafe. Thanks for coming.
My pleasure.
So, I give you now the presentation and moderator role, and please also tell us everything you want. And
yes, I'll share my screen now.
Yes, we see it. Perfect.
Okay, great. Today, as Carmen already mentioned, we are here to discuss how we can build chatbots trained on custom data. And we are going to do that step by step. I'm going to start with a bit more detailed intro about myself. Then we are going to go through some developments in the field and industry, how we got here, and to show you that these things are not as new as you might think. Then we are going to discuss the current limitations of large language models and what are the possible solutions that we can utilize to overcome them. We're also going to explore a bit vector databases and finally the RAG architecture, which basically allows us to build chatbots or conversational models, let's say, with the context knowledge of whatever we wanted to know. And if we have time, I hope we will, I will show you a live demo of a no-code architecture and solution, just to showcase the difference between just using a plain LLM and then using a RAG architecture. And my objective, I hope, for the end of this presentation is to allow you to better understand how LLMs can be used with custom data to serve very specific needs. And this could be specific context, specific domain knowledge, a set of proprietary or private data, etc. A bit about me. I have a developer background. That's how I started my career as a developer. I did that for about 3 years. Then after completing my master's in business information management, I moved into product manager and project manager roles. I'm currently based in Bulgaria, but I lived 8 years abroad. And while I was abroad, I was mainly working on various ventures as an entrepreneur and founder. I've started I had 2 different consulting agencies with different people. The first one was just for software development, but then I decided to specialize more into AI. This was in 2018. And with my colleagues, we worked with small and medium enterprises, as well as governmental organizations, and even some of the biggest NGOs you could find. And this entrepreneurial experience allowed me to gain knowledge and a skill set from a development and engineering standpoint to product management, product development management, sales, marketing, events, strategy, etc. And currently, in addition to my other work, I'm also doing a PhD. More specifically, my PhD research is focused on simulating processes, generating synthetic data, and then using that synthetic data to train other models. So the whole process. Okay, let's start. So how did we get here? We're going to explore the evolution of machine learning very quickly. Just to give you a better understanding of where all this is coming from. I'm going to start with transfer learning. Transfer learning was a very hot topic 4-5 years ago. And basically, back then, we were training models. For example, let's look at a computer vision model. We were training models, obviously, of course, with a lot of data. So if we look at a model that can detect automobiles on a car road, we need a lot of images, right? Labeled images to train the model to be able to detect these vehicles. However, using the exact same model, but fine-tuning it on a much smaller data set would allow us to repurpose it. So in this example, if we have the model that has been trained on hundreds of thousands of images of cars, we need a much smaller data set to repurpose it to identify golf carts, for example. Now here the 100 images might be a bit exaggerated, but the point is just to show you the difference in the magnitude of data from that we need to train a model really to understand and detect in diverse backgrounds and diverse situations one object, and then much smaller data set allowing us to repurpose the same model to detect similar objects, not the same, not too different, but similar, like a car and a golf cart. And now if we think about this on a much bigger scale, we came to the foundational models approach, which is currently dominating the space. Foundational models are trained on massive data sets, as you can imagine. Everything with AI requires a lot of data. but they are by design structured in a way and trained in a way to be highly adaptable. So if we look at this diagram that I tried to illustrate the hierarchy of AI, we have artificial intelligence as the overall circle. Then as a subset of it, we have machine learning. Not all AI is machine learning. There are some statistical models which can be considered artificial intelligence, even though they are not machine learning. Then we have deep learning as a subset of ML. And as one particular set of algorithms within deep learning, we can train foundational models. So here, this is a concept AI overall. This is a set of algorithms. This is a set of another set of algorithms, and here we start talking about models. So foundational models are what allows us to have this current boom in AI, specifically in generative AI. And large language models are a subset of foundational models. This is because foundational models could be image focused, for example. So if we look at Stable Diffusion or the Midjourney models, DALL-E, Adobe Firefly, these are all image generation models. They're still foundational models. And why we call them foundational is because we train them on a lot of data, and they're able to do a lot of different things. Even though it's the same activity, the context could vary a lot. So with DALL-E 3 or whatever, all of the image generation models, big ones at least, you can generate an image of a cat, but you can also generate an image of a dog or an image of a skyscraper, right? So they are not trained on one specific use case. They are trained on as many use cases as possible. Same goes with large language models. When you use applications like ChatGPT or Microsoft Copilot or whatever, you are able to converse with them on a variety of topics, from, I don't know, telling jokes to helping you learn and understand very specific terminology, or even giving you cooking recipe ideas, for example. So they're very diverse, and this high adaptability is at the core. And this allows us to get to these very powerful models that we have nowadays. The GPT-4 or 4.0 now, since 2 weeks ago. Llama 3, which is also brand new, released. And the open source mixed trial models. Llama 3 is also open source. And of course, a bunch of others. I couldn't list all of them, but I hope you get the idea. And nowadays, if you, for example, you can use the GPT-4 model for a very specific case. If you go to a, let's say if you go to Duolingo, right? It's a language learning application for those of you who are not familiar. In that context, the model, the foundational model, is fine-tuned or trained on the very specific context of learning a language. So within Duolingo, you won't be able to use the model in a way that's outside of this context, or you shouldn't be by design. So this is foundational models. Now let me very quickly explain how large language models work. They're basically a next word predictor. This means that even though when we chat with ChatGPT, which is an application that's built on a GPT model, over a GPT model, it's a wrapping application basically. We interact, we send our request, our prompt to the model, and the model tries to give us an answer that statistically has the highest probability of being the best answer. So this means that the model thinks word by word, what is the best word following the previous one, or what is the best sentence following the previous one. The model doesn't think, at least not yet. Very soon, I believe, we'll get to a new level of language models that think on a much bigger scale. But as of the moment, most of these models, they are predictors. They think about the next word, the next sentence, and that's the scope of their thought. This is why, even with the most sophisticated models, sometimes we get repeated information within different paragraphs, or even sometimes within the same paragraph, we can have a very similar sentence. It's because the model is still thinking, oh, it's best if I repeat this, or if I say it again, maybe with slightly different words. Okay. So what are the limitations of these models? Probably you know some, and the most popular one are that the most popular limitation is that they're unreliable, or this means that they have, depending on the context, they have a chance for hallucinations. And a hallucination is the ability of the model to produce unexpected information. This, why I say unexpected, is because it could be a wrongful set of information or a wrongful answer, or it might be true but outside of context, right? So depending on the use case, this level of hallucination can vary a lot. Even though, as I already said, foundational models are they have it in their design, in their core, to be highly adaptable. They're highly adaptable on public knowledge, on common knowledge. They are not as easy to adapt on very specific domain knowledge or specific information, and I'll show you in a bit why. And one of the main reasons is they're missing context. So probably some of you have heard that what the public information on the internet is just like 10-20% of all the information on the internet. And the reason is that everything else is proprietary. So we have trained a large language model, which is a foundational model by design. We have trained it on all the public data, but it doesn't have any idea of our corporate data, for example, or I don't know, if we take the example of a school, it doesn't have any idea about the different students or the curriculum or the tests that are specifically for that school, unless that's public data, and most of the time it's not, right? So missing context, difficult to adapt. And also this leads to lack of specialized vocabulary. Sometimes in specific projects or in specific domains, we might be using certain terms that the LLM has no idea about. And this could be very, very niche. It could be project specific even. So yeah, it's limited. So how do we solve this? The more established way, the thing that we have been using for the past couple of decades, is fine-tuning. Fine-tuning is basically the process of retraining a portion of the model. I'm going to try to not go too deep into the technical explanation here, as I know there are some people who don't have the engineering knowledge and background in the audience. But if this diagram looks scary, it's not. We have the massive data set. We pre-train the model, so we get the LLM. This is, think of it as GPT-4, for example, or Llama, whatever. Then we have our domain-specific data set. We do the fine-tuning, which is the retraining of the portion of the model, so it knows our context, our domain-specific information. It has awareness of it. So we get to the fine-tuned model, and this is what our users use. Or slightly more technical explanation. I know this might look even more scary. I'm going to try to very quickly explain. Basically, we have the pre-trained model, and we want to fine-tune it. The output layer, you don't need to know what the layers are in the model. It's irrelevant for this presentation, but basically the output layer is what the user interacts with. This needs to be trained from scratch, while the information within the model, the knowledge of the model, has to be fine-tuned. So if we look at the model, if we make the metaphor that the model is like a human brain, we need to still teach it a lot, right? It's like teaching someone a whole new set of information, a whole new set of knowledge. And this might take a lot of time. And these are the limitations of fine-tuning. It requires substantial hardware and computing power, because it's still very compute intensive. It's not as heavy and as complex as training a model from scratch, but it's not easy either. This results in a lot of computational costs, time and money, and as well as expertise. It requires very specific expertise to be able to do that, not just for machine learning knowledge and data science knowledge, but domain-specific knowledge as well. Then we have other things that people were currently trying or have been trying in the past few years, like Ph.D, parameter efficient fine-tuning, which is slightly better. This basically allows us to train not the whole output layer, but as we saw just a couple of minutes ago, but just the specific parts of the model. We try to like brainwash it and just try to inject these small pieces of knowledge and replace the existing knowledge. It's still fine-tuning, but on a smaller level, on a smaller scale. It's still expensive. It still requires periodic fine-tuning, and because otherwise it will be outdated very quickly, the knowledge. There's limited transparency of where the information comes from. So it's difficult to explain to the user how the model came to a specific outcome or conclusion. It still has high level of hallucinations. So it's still prone to giving us wrong answers or out of place answers. And that's when we get to quote unquote the new kid on the block. And I'm quoting because it's not that new, even though everyone's currently talking about it. It's been around for a few years. More specifically, 4 years. It was first mentioned and introduced in 2020 by a group of researchers from Meta, the company behind Facebook and Instagram. And RAG stands for Retrieval-Augmented Generation. So, said in a bit simpler words, we have the generation capability of the model, but it's augmented through retrieving certain data. We'll see what this means in a bit. So suddenly, people start thinking or start saying that fine-tuning is really too expensive when you have RAG. Why is that? Well, let's take a step back and let me very briefly explain a couple of concepts. First one is the semantic search. Most of the search that we perform digitally is lexical. So I'm not talking about Google search here. I'm talking about any database most database queries, or like if you land on a website and you want to search within that website, most probably you're performing lexical search. Lexical search means that the system is looking for literal matches of the query that you have given it. So it doesn't have the hidden meaning behind, or the additional meaning that your words might have, and I'm gonna illustrate that in a second. But it just tries to match it, sometimes even case by case. So if you write something in capital letters, it's possible to not even find the right match. While semantic search, on the other hand, focuses on the meaning of what you're searching, the content behind the search. I'll illustrate really in a second with more of visual representation. But the process is you have the user query, the system analyzes that query. You have a model that does that. It extracts the contextual knowledge behind it and the meaning, and it searches in the database the meaning, for the meaning, not for the exact words that you wrote, but for the meaning. And yeah, this is basically describing the process of semantic search. So let me explain how semantic search works. And to do that, I need to tell you about embeddings and vector search. So embeddings are these digits here in these brackets behind some of the words that I have written here. These digits represent a specific measure of distance, or said in a more simpler, better to understand way, they represent the relative meaning of the word compared to all other words. So I'm going to give you another example in a bit how this works, but think of it like allowing the system the knowledge that a dog, a doggo, and a puppy are very close together, much closer than viper and python, or a wolf even. And that tea, coffee, and sugar, even though they have almost no lexical similarity as words, they have very common meaning, and they are not even synonyms referring to the same thing, but they can be very easily used within the same context. And we as humans have an innate understanding of that hidden meaning of the words, while computers and models struggle a lot to extract that meaning. So this kind of embedding allows that. So how does it work? For the engineers in the audience, very briefly, embeddings are projections of sparse, high-dimensional information onto dense, low-dimensional representations of data optimized for AI algorithms. Or, if I try to simplify it a bit for the non-engineers in the audience, basically, just any common way of representing a word brings to the machine, to the system, a lot of fluff with it. So we optimize it, we remove, think of it as removing the hell of a lot of unnecessary zeros in the 0 and 1 combinations that they might have, and just getting to the actual meaning of the word. I'll show you in a bit how that works. But the natural question that probably comes to your mind is, how do we get to these embeddings, to these digits that represent the distance to the relative words around it? Well, it's through an embedding model. So again, we use AI to train. We use an AI model to do that. And at least nowadays we do that most of the time. But there are much slower ways to do it without AI. But here's an example where I'm calling the OpenAI embedding model with the words "Hello AI Cafe." And because the embedding model of OpenAI has 1536 dimensions, and the dimension is basically each digit here, each floating number, it gives me 1536 numbers that represent that specific phrase. So, hello AI cafe is human understandable. Machine understandable is this thing here. And I've cut most of the 1536 dimensions just to illustrate. So, coming back to this picture, if you remember it from a few minutes ago, this allows the system to know that tea, coffee, and sugar most probably have a very similar context in how they're used. It allows the system to know that Python and C# could be used in any programming context or computer science context. But at the same time, Python and Viper could also be used in a context related to snakes, right? Or this whole thing that circles around all the fish word, all the sorry, all the animal words on the screen, including fish, giraffe, wolf, and the 3 dog words I've written. This allows the model to know that, oh, these are animals. And just to give you an example, the words fish and fist, lexically, they're almost the same word. They have the same length, 4 letters, and only the last letter of the word is different. We have H here and T here. So to the system, if we give it this, it will think that fish and fist are most probably very similar words. We as human know that they are not, and most probably have almost no similar context between the two. At the same time, we know that fish is much closer to giraffe in its meaning than fist is to giraffe. And it's because fish and giraffe are both animals. But lexically, giraffe has almost nothing in common with fish as letters. Just the second letter is the same. So again, this allows us to train the system to understand the additional meaning that the words bring. Or in this example, if we look at the 3 dog words, dog, doggo, and puppy, now try to look at the embeddings. These embeddings, as you can see, are different from each other, but quite similar. We have 0.1, 0.1, 0.3, 0.51, 0.55, 0.5, right? Very similar. Now look at fist, minus 2.1, minus 2.55, right? This is the distance that I was talking about, the distance of the meaning. Okay, hope this makes sense. Now, if we are going to represent language data especially, but also just all kinds of data, if we're going to represent it in vectors like this, or embeddings, these are vector embeddings, we also need a whole shift in how we store, manage, and process these embeddings. So this is where vector databases come in. Relational databases struggle with storing this kind of meaning and matching the distance properly between the different embeddings. I'm oversimplifying it here, but especially if we put this on a much bigger scale, traditional relational databases struggle a lot, and that's why we need a whole new way of doing it, and that's where vector DBs come in. So again, we have our data, we run it through an embedding model, we create the embeddings, and then we store those in the vector DB. Very simplified process. Okay, now this is an architectural diagram of RAG, Retrieval-Augmented Generation, remember? Might look somewhat intimidating to some of you. I'm going to try to oversimplify how it works so it's easier to understand to as many people as possible. You have your knowledge base, and this could be anything. It could be your company data, it could be your whatever proprietary data you want the model to have familiarity with. Then you have your user. The user interacts with the UI. Think of it as ChatGPT, for example. ChatGPT is a UI application allowing you to interact with the model behind it, the GPT models. So the user sends a query through the UI. The UI sends that to the embedding model. The embedding model, as we just saw, is this thing that turns our text into embeddings. So it embeds the query of the user. And this is sent to a retrieval model. That's a second AI model we're talking about here. This is caching, just to avoid every time calling the model. So we have the embedding model sent to the embedded query, sent to the retrieval model. Then the retrieval model compares the embedded user query, so the user question turned into numbers. The retrieval model doesn't try to find the exact matching numbers. It tries to find the most similar and closer numbers within the vector database that stores all the embeddings that we have given it with our knowledge that contains our knowledge base. So specifically, the knowledge base goes through all the data we want to give it, goes through a text splitter just so it's split it into smaller chunks. It goes through the same embedding model and that turns it into numbers with specific distance, and that's stored in the vector database. So the retrieval model compares the numbers of the user's question to the numbers that it sees in the vector database. It gets the most relevant results, creates the prompt for the language model. So until this point, we still haven't prompted the language model actually. This happens before we prompt the language model. The retrieval model gets the original user question, adds to it the extracted information from the vector database, and sends that to the language model. And now the language model, having the question of the user plus the actual data that might contain a very similar meaning with the question to the question, it forms the output, and this is sent back to the user. So basically, why is this good? It allows us to give the model, the language model, context and additional meaning it might be lacking without having to retrain it all the time. This is why I've also included a schedule update here, because just by regularly updating the vector database, we have up-to-date information in this system. This means that we don't have to every day fine-tune the language model so it has the latest data. We just give it the latest data with this process. And we ask the language model, again, this is the question that the user asked. This is the latest data that answers that probably might contain the user's answer. Please answer the user. That's where the output comes. I'll show you in a bit. I hope we have time for the demo, how it actually works, so you see it in action. So what are the pros and cons of RAG? It minimizes hallucinations. And the reason is, within the same prompt, we basically say, here's the question, find the answer in this piece of text. So we limit it tremendously. This allows for the level of hallucination to drop a lot. Like, I've seen some benchmarks saying that this allows 80 to 90% lower chance of hallucinations. It very easily adapts to new data, so as I already mentioned, no need for fine-tuning again and again and again. We just need to update the database with the latest knowledge, and we'll have it within the conversational system. It's transparent because the model receives the information as part of the prompt that the user will that will contain the user's answer. It's very easy to configure the model to even give you as a source of information where it got the answer from. So it's much easier to be transparent and interpretable with this kind of architecture. And obviously it's much cheaper if we do it this way than constantly having to retrain the model. Well, as anything else, it has its own limitations, of course. Even though it sounds like a very easy fix, it doesn't fit all contexts and all use cases. It's still not enough sometimes. And it's highly dependable, even more so probably than fine-tuning, on high quality data. Overall, all AI systems are highly dependable, high quality data. This is why we have the garbage in, garbage out saying. So if we put garbage data, you'll get a garbage answer. So it's highly dependable on the data quality still. And we are at the demo time. I'm going to show you a short demo now, how this works in practice. To do so, I'm going to use this tool, Flowwise. Flowwise, I'm not in any way affiliated with them. It's an open source tool that allows us with no code approach, just drag and drop, to build concepts and proofs, POCs, proof of concept, of such applications. And to install it, you just need to go to its GitHub, install it locally, and you should be done, able to use it. So I'm gonna start it now on my local server. Okay. So this is what Flowwise looks like. Again, it's an open source built on top of LangChain and Llama Index, which are both frameworks for LLM applications. They're both open source. This is open source as well. So we have this marketplace where we can get templates from. It's free to use, by the way. So if I go here and I say simple chat engine, can use this as a template. I'm gonna make some changes here. Just so I can use ChatGPT. I have or the GPT models. I have already configured my API keys. I'm not going to bother you with that, but this has a connection to my OpenAI account, so it's able to call the OpenAI API, and we can even choose which model to use here. Let's use the most powerful GPT-4. GPT-4 is not available yet here, I think. And I guess this should work. We save it. We say AI Cafe demo. No, let's call it AI Cafe simple chat. Let's see what will happen. We saved it and now we can call it. Hi. It works. So Let's see, tell me a joke. So it's able to answer. So let's ask it, what is rug? So as we can see, it doesn't have the context from which I'm asking it. It gives me 5 different ideas that are all not what I'm asking for, right? This is an example of the lack of context that I was talking about. Even though it's a very powerful model, it has a lot of knowledge behind it. It has no idea what specifically I'm asking it about, right? Okay. And just to verify, it didn't say anything about the rack architecture that I've been talking about. Gives me some other things. So now we go back and we create this thing, conversational retrieval QA chain, this one. I'm going to use this as a template. I'm going to change. So this is, let me explain a bit. This is basically a very similar architecture to what I showed you in my presentation. This is the conversational engine. This is basically what the user interacts with. It connects to the LLM. This is the LLM. And here I can configure the temperature, which is basically how much freedom I give it to be creative or stick to the specific context. I give it my credentials. Pinecone is the database, the vector database that I'm using for this. I haven't opened Pinecone here, but it doesn't matter. Pinecone is the database I'm using for this vector database. And I'm also going to put my credentials. This is the embedding model. So this is what allows to turn the user query as well as the provided information into vector embeddings. Here, this I'm going to change. This is just allowing me to upload a text file. I'm going to change it to a PDF. I connect it to the vector database. And this is the text splitter. And that's what cuts the text that I'm going to provide into smaller chunks. So the chunk size is 500 tokens. The overlap is basically how much each chunk overlaps with the other ones, with the previous and the next. Okay. I think I have a file which I'm gonna just a second show you. Okay. So I have this file, which is basically the latest updated version of the original paper that described what RAG is. The one that I already told you about by the Meta research group of researchers. So it's the original one was from 2020, and this is the updated version, the amended version from 2021. So I'm going to give that to the language model as knowledge base, and I hope it will work because it doesn't always work. Again, this is a good tool for proof of concept. This is not anything that I recommend being used for production. This is just for demos and proof of concept, just to show you how it works. Okay, then we need to provide our Pinecone index. And I'm going to create a new one. The indexes in a vector database are basically the tables of the database. Think of it like that. We'll call it AI Cafe Test. I'm going to create it. In the meantime, by the way, if you have any questions, just write them in the chat and I'm going to answer during or after the demo. So our index of AI Cafe Test has 0 vectors in it right now. So it's basically empty. We will give this to the Flowise application. we're going to save this as AI Cafe Rack demo, and it's saved. This allows us to send the document or the embedded information of the document into the rack, into the vector database. And now if we check the database again, we have 159 vectors in it. So it should have the information we wanted to have. So let's see how it works. Oh, we're going to change the model here. Let's go with GPT-4 again. And let's do the exact same thing. Hi. Okay, it answers. Tell me a joke. I always like to test. It's not sure. Maybe it already thinks about the context of the document. Let's see. What is rack? Let's see if it's able to answer at all. Natural language processing. Okay, it says that it has some understanding of rack, but not a specific definition. What does rack stand for? It struggles to answer this. But in any case, we at least are able to give it a context. Now, with smaller documents, and maybe if we change this to a per file and not per document, per page, to have a higher understanding. And I'm gonna send it again, see if it will change its answer. Again, just for demos, right? Just for proof of concept. Yeah, okay. I can try to wipe this and do it again. Again, if there are any questions in the meantime, let me know. We're almost at the end of the demo. I'm gonna try one more time. I'll call it AI Cafe Test 2. So I wiped the previous table in the database or the index, and I'm creating a new one. It has, again, 0 vectors. Oops. I'm gonna save it. I'm gonna wipe this conversation so we start from scratch. And I'm gonna send the data to the vector database again. Okay, let's see what it's gonna say now. Okay, well, even though we have a demo fail, I hope that you get an idea of how this is able to provide it with more context. And I was looking at another way to do so. There's just this Databricks explanation of rack. So if I download this, let's try it. I'm gonna download this page. And we have the new text file. And I'm gonna provide it to the document, save the architecture, send it again to the vector database. And I hope it went through. Maybe not. Let me see. Let's see if this will work. Okay, the vector count at least increased here. Let's wipe it again. change a bit the chunk size. Oops. I'm gonna keep it to 1,000 this time and see if it will have any difference. Yeah, okay, whatever. But basically, in a proper system, this will give it its own context awareness, and it should be able to answer within this particular context what the basically what my question was. I just lack the proper document to show you this. But if we have any in any other context, so this is very complex, very scientific context. But if we have, for example, information about an event, so the LLM by itself, it wouldn't have information about the event itself, right? So if it's an upcoming event, for example, and if we give it the event information, we can ask it questions about the event with no problem. Because we are running out of time, I'm gonna stop that here.
I have a question. May I ask it?
Yes, of course.
From the audience? Yeah, because we have a question. Yeah. Thank you for sending questions. Hi, I have a question. I'm a legal consultant, so thank you first of all for your non-technical explanation as well. This was very helpful. A question I will sometimes get from clients is that they would like custom LLMs based on their own internal documents, like their own abbreviations and their own processes. However, we generally advise against inputting client data into LLMs for safety and confidential reasons, as we do not want the LLM to reproduce that data for another third party. Forgive me for my perhaps non-technical question, but is there a way Rak could help with these questions? Thank you.
Of course, it can help. And if you're referring about LLMs like the GPT models behind ChatGPT, I would also advise against inputting sensitive data there. But if you're running your own LLM locally or in the cloud, then it's a matter of how secure your network is or your environment. But overall, for non-public LLMs, as long as it's secure enough, you should be able to give it any sensitive information. It's really just a matter of permissions and how secure your network and environment is. RAG can help with this a lot, for sure. It will allow you to give it the context of the specific project or client without having to fine-tune and constantly retrain the LLM.
Okay, thank you. And then question, how is evaluation done, especially conformity to the European AI Act?
That would happen on a few different levels, I would say. Again, that's not in any way related to what architecture you use. Whether you use traditional fine-tuning or RAG, it doesn't make much of a difference in terms of compliance to regulation. My advice for compliance to regulation would be on a few different levels during the project's lifecycle. For example, it could be done beforehand. It could be done after the preparation of the data, and then after the work on the model. Whether it's fine-tuning, whether it's providing it with the context through the RAG architecture, it doesn't make a difference.
Okay, thank you. We're coming two more, and then and then we cannot accept questions anymore as the time is running out. But thanks a lot for the very interesting presentation. So that question is not just a congratulations. I'm developing here, new question. I'm developing an LLM fine-tuning 18 model for question answering tasks, and it must run on a Raspberry Pi, which I already did, and it works. but I'm struggling with the hallucination problem. Do you think rack architecture could run in a low réseau, when it's cut off, low resolution, I think. Let me see what it means in a low resolution. Yeah.
It can definitely help.
In a low resource system like Raspberry Pi.
Honestly, I'm surprised that you managed to run a large language model on a Raspberry Pi. It's a feat by itself. So congratulations on that. The Retrieval-Augmented Generation architecture will run before, basically the embedding and the retrieval model will both do their work before calling the LLM. So you can host your LLM on the Raspberry Pi. You can host the embedding model and the retrieval model on a different hardware server or in the cloud, it doesn't matter. And they are basically, in their work, as I showed in the architecture diagram, through their workings, they will prepare the prompt that will be sent to the LLM. Probably running it on the same Raspberry Pi wouldn't be advisable. It might be too heavy.
Okay, thank you. Yeah, due to time, do you want to say a last word? Because we stopped you with all the questions.
Yes. Let me see. Can you see my screen?
Yes, building chatbots, thank you.
Yeah, okay, great. Yeah, you can connect with me on LinkedIn. This is the QR code. You can scan it and find me there. If you have any further questions, don't hesitate to send me a message.
Yes,
thank you.
Thank you for showing up. Everybody today in the cafe, please come back and also feel free. We have still some space for speakers until the end of June. So if somebody in the audience feels like I have to say something, please apply to me. And thank you and have a nice afternoon. And I will send the recording to you, Bobby. If you like it, you give me green light, else you say no. And then we publish it on. Okay. See you.
Bye, everyone.
See you. Bye.